Okay, so again, good afternoon, everyone, and welcome to the quantum key distribution and post-quantum cryptography lecture. Okay, so by the way, I'm Vincent, and I will be your host for today. Okay, okay, before we officially start, so let me introduce first who is One Quantum Philippines. So One Quantum Philippines is supporting the Philippines in transitioning into the quantum era. So we empower Filipino talents in quantum, moving the quantum frontier one qubit at a time. Okay. So that is One Quantum. So we are a nonprofit organization focusing on the um providing educational resources and support to Filipino talents who want to explore the field of quantum computing. Okay. So so before we move to the introduction of our speakers and the lecture proper, so please let me remind you of the following. So first is stay till the end. The feedback form will be sent in the chat after the lecture. So your feedback will is requested before being given the certificate. And we have an open Google Slides for collaborative note taking. This is optional participation, and the notes will be sent to your email along with the certificate. Okay. And aside from that, if you want to also take notes manually, you can do so. Please prepare pen and paper na rin if you prefer that kind of notes. Okay, so now let's move on to the introduction of our speaker. So our first speaker, okay, he is a visionary leader and president of One Quantum Philippines and a member of the Quantum Technology Board. An architect and software engineer with a storied career from Section 6, Globe Telecoms, Deutsche Bank AG, and Red Hat, and advocacy on making quantum computing accessible in the Philippines. So, let's give him a warm virtual round of applause for Sir Bobby Corpus. Okay.
Thank you. Thank you, Vincent.
And by the way, that's not only we do not only have one speaker because we also have another one. Okay. So our second speaker, he is an experienced innovation and R&D engineer in various leading companies in Europe with 15 years of innovation experience in the fields of defense and space, operating systems, and secure devices, and 10 years of experience in cryptographic protocol interaction. So let's give him a warm virtual round of applause for Sir Earl Robles. Hello po, Sir Earl. Hello, Sir Bobby.
Thank you. Thank you, Vincent.
Yeah.
Thank you.
You can hear me, right?
Yeah.
Okay. Thank you again.
Hi, Vince. Are we gonna proceed now?
Yeah. Hello. Hello po.
Hi, Vince.
Yes po, Sir Bobby.
So are we going to begin now?
Yes po.
Shall I share my screen now?
Yes po, Sir Bobby. And so while waiting for the materials, Mhm. And I would like to ask everyone in the chat, so how was your weekend? Yan. Super init ba? Yan.
I have a
Yeah, I heard like 40 plus heat index for the consecutive weeks na, no? Yan. So, also, ayan. So, habang nag-lecture, please, ayan, don't forget to rehydrate. Ayan. Need natin yan while having this lecture.
Okay. Yeah, so hello. Thank you for attending this. I think this is our first meetup for the year. And I'm going to talk about quantum key distribution. So in the quantum era, which will be which they call the what you call this days to quantum or years to quantum, y to q. There is this threat of our encryption systems to be attacked by a quantum computer. And so there must be some way for us to protect ourselves. And so the foundation of the security is really what is known as a perfect security, which I'll also mention later. But currently, our cryptography, most of the encryption that we are using currently are based on what is known as the RSA, or the Rivest-Shamir-Adleman cryptography, which is based on the hardness of factoring very big numbers. And there is this paper which says that a 2048 bit encryption can be decrypted in using a normal computer in 300 trillion years. So, well, that is actually the more than the age of the universe. So, which means that we are very safe in terms of RSA, except that in the quantum era, when we have the quantum computer, which is the fault-tolerant quantum computer, scalable fault-tolerant quantum computer, it will be very easy for this for the RSA to be cracked by the quantum computer. So so there must be a way for us to protect ourselves, and there are actually two ways, at least two ways. One of them is the quantum key distribution, and the other one is the post-quantum cryptography, which Earl is going to talk about later. So yeah, so let me just time myself for 20 minutes because I'm supposed to be doing this for 20 minutes. So let's start. We're not gonna review that. So almost everything that we do, all of the transactions, all of this commercial transaction, whenever we buy in Lazada or Amazon, these are all encrypted. And so it's like most of it's like the foundation of the information age. Without that, a lot of things there will be chaos. So cryptography is there for us to maintain the secrecy. And actually, it's not only encrypting something, but also being able to prove that you are who you are. So it's authentication and non-repudiation. So, but so we know that there's a lot of things also going on, like the in the cybersecurity world. There's it's like the virus and antivirus. Like some people create virus, and there's also antivirus. And in the cryptographer, in the cybersecurity world, there are people who secure the systems, and there are also people who try to crack the systems. Yeah. So now, in terms of in terms of encryption, so we already know we know that for example, the RSA analytic curve, they are susceptible. They are susceptible to quantum computing attacks. And but the thing is there really such a thing as something that is not breakable? So it's something unbreakable that even a quantum computer will have a hard time, will not be able to break it. So whether you're mathematically gifted, computationally advanced, algorithmically advanced, is there such a thing that something which you cannot break? Okay. Well, actually there is, no? So it's called the one-time pad crypto system. So it's been proven to be a crypto system with perfect secrecy. So which means there is no correlation between the ciphertext. When you say ciphertext, it's the encrypted text and the plain text. And this one, and there's an implementation there called the one-time pad, and which was used in telegraphy. And so it was first described by Frank Miller, and then it was patented by G.S. Vernon of AT&T. Now, the thing about one-time pad crypto system is that the number of bits that you need, that you have to encrypt, should correspond to the number of bits of your encryption key. So it's 1-to-1, and then it assumes that you have a truly random what you call this, generator, no? So for example, in our computer we have a pseudo random generator. So these are generators of numbers with a very high period. So very high period. So which means that when I say period, it will repeat itself. So someone who's clever can actually possibly crack a pseudo random number generator. So what we are for the one-time pad, for it to be secure, it has to have a truly random bit generator. Okay, so here's an example. Okay, just see. Here's an example of a one-time pad crypto system. So suppose you have an alphabet, okay? So suppose you want to encrypt a message, based on the alphabet and the letters and this special and this punctuations. So what you do is to map them first to numbers. Like for example, that's what I'm doing here. I map them to numbers, and then you create a private key. Okay, so this is the private key that so the private key should be pre-shared. Okay, so for example, if I'm Bob and I'm going to send a message to Alice, Alice should also have the same key. Okay. And then, for example, here, prepare the message. My PIN number is 1234. And then, so this is your message. And what you do is to map this into the numbers. So the letters will not become numbers. And then the encryption is like this. For each number that you get, you compute the ciphertext. Okay, you compute the encrypted or the number, the resulting encryption. So the formula is like this. Whatever is the message, you add here another number, and then you get the modulo. Okay, modulo of where L is the size of the alphabet. So here the size of your alphabet is the number of characters here. And then when you decrypt it, you just do this formula as well. Okay, so let's have an example. Okay, so for example, my PIN number is 1234, and then we have a bank character here. So you compute to compute the ciphertext, first you map this message into numbers, okay, which is what we are doing here in the previous slide. And then for each number, you use this formula, okay. So here, this is your ciphertext, right? This is your message that corresponds to the number that corresponds to your letter. And this one here is the key. So for example, if you are at the first, for example, if I is equal to 0, which means is the first element, then here Ki is 38. Okay. Oh, sorry. Ki is, what is our number? Okay, Ki is 30, and then 57, 26. So that's a private key. So this one is our message, 38, and then you add 30, and then you get the modulo 76, and then your ciphertext is then 68. And then you do this for all of the numbers, and after that you just convert it back to text, and that is your secret message. So in order to decrypt that, once Alice will get this message, what she will do is just use this formula. Okay, so whatever is the encrypted text, encrypted text, subtract it with the corresponding key in that position, plus L, and then modulo L. Okay, so that's an example. Now let's have another example using the bits. Okay, so XOR. Now suppose you have a binary number, okay, like this. Okay, so everything turns to binary, and then the key that you arrange with Alice is this one here. Okay, 0, 0, 1, 1, 0, 1, 1, 0, 1. In order to encrypt this is your message, right? The message mo. In order to encrypt this, you just have to XOR. Okay, so XOR 1 XOR 0 is 1. Okay, 1 XOR 1 is 0. Okay, and then 0 XOR 1 is 1. So 1, and then you do for all of the digits, and then you get this encrypted text. Okay, this is already your ciphertext. Now, how do you decipher this? Okay, so since Alice also has this key, what she will do, and then we will send this to Alice. Once Alice gets this, she will just reverse the process. Okay, so this is your encrypted text, and then you XOR it with this one here, and what you do is you get the original text. Okay, so 1 XOR 0 is 1. Okay, 0 0 1 1 1 1 0. Okay, so as you can see, this one here matches the original text. Okay, so In other words, with a one-time pad, if we know how to execute it properly, then we can have perfect secrecy. Now, the thing that to consider about the one-time pad is that, as I mentioned earlier, you need to have truly random generated bits. Okay, and then the secret key cannot be reused. No? So once you use the key, you have to destroy it. Okay, it cannot be reused anymore. Otherwise, some clever cracker will be able to decipher your message. And then I think the most important thing here is that how do you distribute your keys? Okay, given that you cannot use the same key uh, uh, in another encryption session. So the distribution of keys is really the challenge in one-time pad. No, kaya it is not widely used. The one-time pad is not widely used because first, how do you distribute the key, right? Either how would you do that, right? So either you use, for example, RSA or elliptic curve to distribute this key to Alice, or else you can also meet with Alice face to face. No, so you agree on the key. Now, and also the thing is, this one here, the truly random generated bits. Now that's really a big challenge as well. No? So now the QKD is one of the ways in which we can generate the keys and distribute it securely. No? Okay, so QKD. So quantum key distribution, it uses the mechanism of quantum theory. So the thing about the quantum theory is that it's a very successful theory, you know? And whenever you prepare a state and someone will try to observe that message, no, that you exchange with Alice, what will happen is that the state of that thing that you're exchanging with her is going to be different, no? And it will destroy the state. And there's quantum key distribution has a protocol which will allow you to determine if someone is eavesdropping. So in the cryptography world, there is such a thing as what you call this. The characters there are Alice and Bob and Eve, the eavesdropper. So there are many protocols of quantum key distribution, but we are going to discuss only the very first one because it's very simple to describe. And it uses the quantum property of known as polarization of photons. Okay, so a photon is an electromagnetic, a stream of photons, electromagnetic wave. No? And so an electromagnetic wave is composed of a electromagnetic, electric wave and a magnetic wave. No? So the electric wave is perpendicular to the magnetic wave, and the direction of which the magnetic wave, electric wave is oscillating is called the polarization. So there are three kinds of polarization. First is the linear polarization. So ito yung polarization that we will use in QKD. The others, circular polarization, elliptical, one is just the generalization of the other. So elliptical, circular polarization is when the electric wave is oscillating in a circular manner um, on a plane that is perpendicular to the direction of motion. Now, so what is a polarizer? The polarizer is maybe if you've heard of the Polaroid, no? So it's quite popular, no? The camera. So it uses a polarizer. No? Polarizer is a device that will allow you to filter light so that only those that are polarized in a certain angle will be able to pass through the polarizer. So, for example, here you can see that there's a source of light here, and it emits photons with different polarization. So here you put a polarizer, and what the polarizer does is to prevent the other photons from going into the filter, and only permit the the one with the vertical polarization. No? So ito yung vertical wave. No? That's the only thing that is being allowed. No? Now, this polarizer is we're going to use this in what is known as the QKD protocol. No? So it's to filter out, and then here, suppose you have a photon that is polarized in the vertical, and then or horizontal. No? So a photon can be polarized vertical or horizontal, or it can be a superposition of both. No? So for example, if you have a photon and polarized in the vertical, and then you have a polarizer which is tilted in the diagonal 45 degrees, what will happen is that the light will the light can still go through. No, the light can still go through, but it will be the output of the photon. The polarization will change into either the diagonal or the anti-diagonal. So itong polarizer na to, no? For example, if you have a photon that is polarized in the vertical, and then you put a polarizer that allows only horizontal, then your vertical photon can never go inside, no? Because the angle of the polarizer is orthogonal to the direction of the polarization of photon. However, if you have a polarizer that is oriented in the diagonal, and then you transmit a photon that is polarized in the vertical, it can still go through, no? But there's a probability that it will be in the diagonal or the anti-diagonal. So it turns out that 20 minutes so fast, no? So I'll try to make this brief, no? Now I'm just going to describe to you the first protocol, the earliest protocol, no? It's called the Bennett-Brassard protocol. So you have two people here, Alice and Bob, no? And then what Alice will do is she's going to get a random number generator. No? It should be quantum random number generator. Kasi yung quantum random number generator, is truly random, no? At hindi siya kagaya, it's not the same as the pseudo-random number generator that has a period, no? So assuming that you have she has a quantum random number generator and it will generate 0 and 1s, no? So bits 0 and 1s, no? And then she will have to transmit this randomly as well, no? So for example, if she gets a bit value of 1, she will try to transmit this in a photon whose polarization is vertical or diagonal. Okay, vertical or diagonal. And if may nakuha siyang 0, she can choose, no, randomly between transmitting this as a horizontal or anti-diagonal polarization photon, no? And all of these photons will go into a channel, no? So this can be a fiber optic channel, and then it will end up in the location of Bob. So ito naman si Bob, what he will do, okay, is he will measure it, no? He will measure the photons, and the way he measures it is like this, no? Random din, no? He will choose between two different orientations, no? The rectilinear orientation. So there are the rectilinear orientation, which means that it can measure polarizations that are in the vertical or horizontal, or in the diagonal basis now, which will also measure, which will measure in the diagonal basis now. So even if you put something there that is not diagonal, like this one here, orthogonal, what you call this, vertical or horizontal, it will still go through the diagonal basis, and it will come out as either the anti-diagonal or the diagonal polarization. Tapos they had to agree, no? If she gets 0 in her random number generator, she will either send a diagonal or horizontal or anti-diagonal, no? If she gets a 1, she will either send this vertical or diagonal. Okay, so there's in this protocol, there are uncertainties, no? So mga probabilities, they had to choose. Okay, so, and that's the beauty of this protocol. So, and then, so as I mentioned earlier, Bob receives the photons and then measures them, no? And when he receives them, he will just pick, no? I'm gonna at random din, no? Okay, I'm gonna measure this using the diagonal. Oh, I'm gonna measure this using the rectilinear basis. Okay, so in order to pick which one, Bob will also need to need a quantum random number generator in order to pick one of those. Okay, now suppose Alice will send a photon in the vertical polarization. Now, once Bob will get this photon, he will decide now, no? Okay, there are two ways he can do, no? So if he decides to measure using the rectilinear basis, so this one will just pass through, no? Will just pass through the beam splitter, no? It will just pass through the beam splitter. Ito pala, may beam splitter dito, no? So it will pass through that. And then since it is itong vertical polarizer went through a rectilinear beam splitter, it means that it will not be altered. No? It will go, the state will not be altered. It will still be what you call this, the vertical. No? Now, paano kapag Bob decided to measure using the diagonal axis, no? Diagonal oriented beam splitter, no? So what will happen is that itong ano mo, photon that is polarized in the vertical, it's actually in a superposition of the states, no? It's actually in a superposition of the anti-diagonal and diagonal states. And then, according to quantum theory, once you measure it, there is a 50% probability that it will end up in the anti-diagonal, or it will end up here, no? So there is a 50% probability. Now, ito kasi, itong this one here, this one is kasi Alice sent this one, right? So this one corresponds to a this one corresponds to a 1, no? Now, so however, kapag Bob measures it using the diagonal axis, he will get either this one or this one, no? So which means that, pero alam natin that this anti-diagonal is actually 0 and this diagonal is 1. So kung makuha niya yung anti-diagonal, he will get the wrong value. And if makuha niya yung diagonal, he will get the correct value. So which means that there's a probability of 0.5%, no, that Bob will be wrong. Okay, so that's the key generation. So the generate ng key. Now, still part of the key generation is after Bob has measured all of the photons, he will then tell Alice, no, this one is the protocol part, no? He will tell Alice, hey Alice, for the first photon, I used the rectilinear measurement. For the second photon, I used the diagonal axis. No? And then see Alice, what she will do is she will take she will take note of all of those, and then she will say, and then for those measurements na nag-match yung kanilang axis, no? Yung kanilang axis of for example, this one here, nag-send si Alice ng diagonal, and then mineasure ni Bob na diagonal, so nag-match sila, no? Or dito, Alice sent a vertical, so rectilinear, and then Bob measured in the rectilinear basis. Alice will say, okay, these are the photons that you have to keep, no? Keep them because we match in terms of the basis that we use, no? Pero someone somewhere, no, who is observing what's happening doesn't really know the basis that they're talking about, no? Kasi Alice will just say, just keep this, no? Kasi nag-match yung basis. Pero someone who is observing, who's trying to decipher the exchange, no, will not know anong basis na ginamit, no? So for all of those bases that match, Bob will keep it, and the rest will be will be thrown away by Bob. Now, this is the part of the protocol where they need to determine if someone is observing them, no? Si eavesdropper, no? Si Eve. So what they will do is like this, no? So now Bob already has all those photons that that match that match with the basis of Alice, no? So they're going to get a subset of that. And then Alice will tell Bob, kasi ganito yun, no? If they match in terms of the basis, no? Alice sends the photon polarized in the vertical direction. Bob used the rectilinear measuring device, no, or beam splitter. It is guaranteed, if no one tampered with the communication, it is guaranteed that whatever bit value that Alice sent will also be the bit value that was sent, that will be received by Bob. Okay. However, if if someone was eavesdropping, then they will not agree na, no? So whatever Alice will say, hey Bob, this is the bit value of the first of this qubit, of this photon that I sent. And then Bob said, oh, it doesn't match mine. So there must be, there must be a either there was some error in the transmission, or there is someone that is eavesdropping, no? Pero but what is the probability na of detecting the eavesdropper? So it's like this, no? So Eve, so she tries to intercept the communication, no? So what she does, so she's like the man in the middle, no, or the woman in the middle. So Alice sends to Bob, but they don't know, both of them don't know that Alice is actually in the middle. Huh? So what Alice will do is intercept the photon that was sent to that is going to be sent to Bob. She will measure it, no? And then she also doesn't know what she will also what you call this, she will also at random pick what what basis to use to measure, no? So she will probably, for example, okay, I will pick rectilinear basis, or I will pick diagonal basis, no? Irrespective, no? Whatever she picks, what will happen is that she has observed the photon. And we know that if the photon is observed, something will happen to it, no? The state will be changed, no? There will be a change of state. The state will not change if she picked the correct, if she picked the correct basis. No? For example, Alice sent a photon that is polarized in the vertical direction, and then she picked a rectilinear beam splitter, no? Then she will get the correct photon, and she will also be transmitting the correct photon to Bob. Okay. However, if Alice sent the photon in the vertical polarization, but Eve measured it in the diagonal polarization, what will happen is that the photon state will now become either diagonal or anti-diagonal, no? And this is, so she has already altered the photon state, no? So, and whatever is the result, she will send it to Bob, no? Tapos, si Bob naman, we'll measure it, not knowing that Alice is in between, no? And we'll either get the correct bit value or not, no? So in other words, in here, the probability that Eve will be detected is pag nagkamali siya doon sa pag-measure niya, so there's a 50% probability that she will have a she measured in the wrong basis, no? So 1/2. Okay. And then when Bob also measures that photon, there's also a 50% probability that he will have he will get the wrong bit value. So because these events are independent, then you multiply them, then there's a 1/4 probability that the bit value that Bob got is wrong. Okay, so which means there's a 1/4 probability that someone is eavesdropping, no? So there's a 1/4 probability that Eve will be caught. So now we go back to the protocol. How will the protocol allow you to increase this probability? No? So but before we go there, so the probability pala na hindi ma-detect, no, si Eve is 1 minus 1/4 or 3/4, no? So that's the probability that she will not be detected. Okay? So there's a big chance that she will not be detected, no? Pero how will the protocol allow you to be able to detect Eve with very high probability? Okay? So this is how it does it, no? So let's go back to the math, no? So if there is a probability of 3/4 that an eavesdropper is not detected, no, in an experiment, then if we conduct n experiments, then what is the probability of detecting the eavesdropper? So if we conduct n experiments, then the probability that the eavesdropper will be detected will not be detected is 3/4 raised to the n, no? So in other words, kasi these are independent events, no? You multiply the probabilities, no? So that's the probability of Eve not detected. If there's only one, then 3/4. However, if there's two, then the probability of Eve not getting detected goes smaller. Okay? So you have to repeat the experiment n times so that you can be sure na this probability will approach to 0. So in that case, the probability of detecting Eve will then be 1 minus 3/4 raised to the n. No? Now, ano yung value ng n so that we have 90% probability na merong nakikinig? So ito yun, no? We just have to solve this and then solve for n. So we have 8. So ibig sabihin, Alice and Bob, they will sacrifice 8 of their photons, no? The photons that they agree on in order to detect if there's a eavesdropper. So now if the probability is very high, no? So they can just scrap the protocol and do it another time. So that's how the QKD works now. Yeah, so well, if you have any questions.
It's now time to drink water.
Yeah, I'm done, sorry.
Okay. Hello. Okay. Thank you po, Sir Bobby. Ayan. So, yeah, if you have some questions, so you can use the Slido link sent here in our meeting. You can type your questions there and we will be having a Q&A later. Thank you. Hello po, Sir Earl. And sorry for the overtime.
No problem. Should I start or
Yes, po, Sir Earl.
okay, I could start. I hope I'm sharing the same screen. So is this the right screen? Can you see my screen?
Yes po. Visible na po.
Okay. Okay. Thank you. So okay, first of all, I want to thank Bobby for inviting me to talk in this workshop. So Bobby and I go way back to UP and National Institute of Physics. So when I was still in NIP and in UP, there were activities similar to this one, you know. So young people like you organizing interesting talks about very interesting topics, given by not so young people. So at that time, I was the receiving end of those talks. So right now, I am one of those not so young people together with you, Bobby. So this is actually a talk, the same talk that I will be giving on Sunday and next week in Silang, Cavite. So when I was preparing this, it was geared towards that audience. So bear with me if there are some things that probably are not so geared towards you, but I will try to skip whatever's not suitable. Menchi gave me the demographics, so I could adjust. So I will ask you questions. Please do type them in the chat so that I will know if you could follow me. Okay. And Vincent, can I would like to ask your help probably to read some of the answers if it's possible. Okay.
Okay po. Yes
So
po.
okay. So next slide. So the outline. This is anticlimactic, but this is the way we do it here in Germany. We we tell the audience what our outline is. It's always like that. It's the way it is. So it's a force of habit. So I'll do it anyway. So first, the first part is the icebreaker. I'll be flashing 7 pictures. Please do guess what those pictures are. Type them in the chat. Vincent, can you help me read out the answers? Okay. Then this will be a prelude to the next, which is part 2. This know why. I will try to convince you why this topic of post-quantum cryptography is very important. Actually, Bobby already alluded to this, and I will convince you some more. Okay. And having convinced you, so we will try to do a little bit of dive. So 20 minutes is not so big, so we could only do as much, but my goal at least is to show you something as an entry point so that probably after this talk, you could go in on your own. So the internet is available to everyone. And I could also probably accept questions, especially when it comes to this topic. And just treat me as one of your teachers, probably. So part 4. So will be the final wrap up. Anyway, so icebreaker clues. So this will be pictures about world history, computing history, and the topic of the talk, which is cryptography, post-quantum cryptography, quantum computing. Okay, first picture. Type in your answers in the chat box. I'll give you 10 seconds. Okay.
We have.
I'll go.
Sorry.
Yeah.
Yeah.
Okay.
We
have
U-boat from Sir Dylan.
okay, very good.
Oh, U-boat.
Very good. Okay. Dylan got it. Okay. Picture 2. Oops. Sorry. Oh, actually, it's written. Okay. What's this?
Yeah.
It's a giveaway.
Another answer from Sir Dylan. Enigma. Enigma
Very
machine.
good. Dylan, ano ko muna? Try, give others the chance. I think you you know this already. Okay. And picture 3. This is not the stock market. If not, I'll ask Dylan. Dylan, what's this? I'll tell you later. Okay. If
We have
okay,
answer.
Dylan.
That's
What?
at World War II.
Yes, very good.
Hit index from NG.
Oh, oh, okay, good guess. But okay, later I'll tell you what it is. Okay, you guys from IT should know this, right? Who's this guy?
Yeah, we have
Okay,
answer.
clue. Have you?
Turing. Alan Turing.
Very good.
Yeah.
From
From Thomas Adrian Nagit. Another answer.
Thomas. Okay.
Similar answer.
Okay,
Yeah,
very
5
good.
similar answers.
Okay, if you watch the movie Imitation Game, you should probably know the story. Okay, this is also from Imitation Game. This one. Okay, so I'll tell you later what this is, but it's related to Turing. Okay.
Yeah.
Okay,
we
this
have
one
answer?
is a giveaway. You know this. Also, did anyone answer?
Yeah. Answer from Ethel Joy Baliang. Turing computer. Yeah.
You okay? Okay. Close. Yes, it's a Turing computer. Yeah. I'll tell you what it is later in detail. Okay, this is a giveaway, of course. Everyone should know this.
Interesting.
It's a topic of our
Yeah. Quantum machine.
organization.
Quantum computer.
Very good. Quantum computer. And last but not the least, okay.
Yeah. Quantum gates.
And
Quantum circuit.
yeah, good. And precisely, it's a specific circuit. Okay, I'll go back to the slides and probably tell you the story why I actually wanted to use these pictures. Okay. So first, U-boot. Okay. This is a fantastic piece of engineering from Germany. So during the World War II, these submarines gave Germany a lot of naval victories. Okay. The way they work, you have the English Channel. It's between the mainland Europe and Great Britain. So it's 75,000 square kilometers. It's smaller than South China Sea, but still big. Okay. Now, the way they work is that they would spread themselves out in this English Channel. So when there is a vessel in that English Channel to be attacked, so one of them detects it. So this one submarine will communicate with the other submarines and say that, okay, I've seen this. There's a vessel to be attacked. Come here in this coordinate. Then they will converge in that point and they will attack the vessel. And that's how they work. And it was very effective. The first years of the World War II was catastrophic for the Allies. So this is how they were really undetected underground. So now the next picture is this Enigma machine, which is another piece of German engineering. This is what the German submarines kept, how the German submarines kept their communications confidential. Like Bobby was saying a while ago, so the eavesdropper, so the Allies who listen to the communication channel. This is underwater, so this is mostly sonar. Okay, you cannot use wireless communication there. So you could listen to this pulses, but you cannot make sense of it. Because why? Because they actually encrypted the payload of the communication with this machine. So it's a form of a polyalphabetic substitution. Well, similar to one-time pad, but it's not one time. That's the problem. So that's a problem. You have an infinite set of possible, not infinite, but a large possible amount of possibilities. It was close to be impossible to be deciphered. Now, okay, then I give you this. Okay, is this okay? I give you this graph, which is not the stock market. It's not a heat index in the Philippines, but it is the the losses of the U-boot. So U-boot, you could see in 1941, there's an inflection point. So mysteriously, all the losses after that rose. Something mysterious. What happened? So came this guy. Okay, if you watch innovation game, imitation game. So Alan Turing is the father of computer science way before practical computers were really not practical, meaning the computers that we know now exist even before the vacuum tubes. So he's a mathematician. He mathematically worked out what a computer is. This is what we call the Turing test before there were actually these machines. Yeah. So in many cases, the mathematics or the logic comes before the technology. So mathematics precedes engineering. If Henry is in the call, most probably he will agree. And this is most of the cases, this is actually true. So, okay, where are we now? So this is, someone said this is the Turing machine. But I mean, more precisely, it is the what you call the machine, which is called the bomb, which Turing did at the University of Manchester at Bentley Park. So there was a secret team of code breakers there, and this machine, instead of being made up of transistors and vacuum tubes, way before back, they used gears. So it's like trying to emulate the reverse of the Enigma machine. So this is the early computer, excuse me, which actually broke the Enigma machine, and that's why the Allied forces won. Excuse me. So it's quite interesting, this story, because when they broke the code, excuse me, you had to pretend that they didn't know, because what will happen is the other side might just change it and they will be back to the square one. So okay, this one is also a clunky computer, which we know now. We are in a similar situation as that of the early days of computing. You have clunky machines, but the math is already worked out theoretically. We know that if these machines, if the technology catches up with the math, it will achieve certain things. And that is what I'm referring to here. This one is a diagram of the Shor's algorithm. It's a circuit, yes, and particularly it's the Shor's algorithm to do factorization, period finding through quantum Fourier transform. We'll discuss that later. So, okay, now having said those stories, these are the answers. Now we'll discuss the know why. Okay, Bobby actually alluded to this. Maybe I'll repeat some of this, some of the things he already said. But probably I highlight things that he did not. Okay, so first is, okay, traditional crypto system. Right now we have two. We're based on two crypto systems. This is the RSA and the ECC. So the thing is, every crypto system is based on a computationally hard problem. Meaning, if you use a current computer, it will take it hundreds of years to theoretically the logic, even if it's the fastest computer available. So currently, it's the discrete logarithmic problem. Okay, why logarithmic? Because according to the math, for example, if you raise something to that exponent, modulo n, modulo is the remainder of this. Can you see my mouse? No? Yes? Okay. So modulo is
Yes,
just
sir.
okay. When you divide this by this, there's a remainder, then that's the answer. The thing is, if you raise something with an exponent and you modulo it, then it will be hard to do a logarithm to derive this e. In a similar way, in ECC, there's a scalar multiplication. We call it the ECDLP, discrete logarithmic problem. It's also hard to know k after you do this operation is not exactly what this is, but there's this operation here that you cannot reverse given the current computers. Now from this algorithm of Shor, okay, this is actually what I flashed a while ago. This is a period finding algorithm that uses a quantum circuit. So in Fourier transform, those who have background in digital signal processing, we know this a lot because we actually, when we analyze signals, we want to disassemble the signal and try to see what are the frequencies. Frequencies are sinusoids with certain period. So in an analogous way, Peter Shor did this for discrete systems with discrete numbers. You see a modulo is a periodic. So you say modulo 5, 0, 1, 2, 3, 4, then 0, 1, 2, 3, 4 is periodic. So that's the thing. So you will be able to derive this period of a certain number system when you actually sample it, given enough samples. Okay. Now, implication of this, it's bad news for RSA because this is the math. When you factor n, the modulo, into 2 primes PQ, you will be able to derive E. This is the totient function. You could look this up later, but this is a very simple math. If you have a composite modulo, you could do something like this, and you could derive the E, which is the the exponent. So bad news for RSA, and bad news as well for elliptic curves. So it's not exactly the same operation, but there's this what you call a group operation of scalar multiplication, and there's this paper. You could, to make the long story short, you could reverse this particular operation when using a quantum computer. So bad news if there's a computer. So bad news for us. Why? Because these are the everyday use cases of quantum computers. Okay, when we write an email, at least in enterprise, in business, we sometimes have a certificate, we sign it, so we use ECC and RSA. When we open our browsers, you have HTTPS. In your browser, it does TLS, it does key exchange. Usually, if it's a modern certificate, it's a newly issued certificate, so it's based on ECC. And if it's an old certificate, RSA. So bad news for browsers. Data encryption. Although, maybe I'll need to modify this. Although, normally for bulk encryption, you don't use these 2 algorithms because they are limited by the block size. What you use them for is to do this key establishment protocol so that both sides, like what Bobby actually discussed, it's like you have a key agreement so that both sides could actually agree with a key, derive a secret key, and without the eavesdropper knowing what is in between. So usually this is Diffie-Hellman. And if, for example, there's a quantum computer, they will be able to derive, they will be able to eavesdrop and be able to as well derive that secret key that you use to communicate with each other. It's bad news. Bad news for blockchain. Now there's a lot of hype with blockchain, and I think locally, I don't know if people even talk about this. Blockchain is actually, especially Bitcoin, is a public blockchain. You download locally, it's distributed. So once it's there, it's there. Now, when the quantum computing computer is already available with enough qubits, so you could actually reverse this ECC operation. And bad news for certain protocols that encrypts data in that chain, not just the signature. So that's bad news. So you'll be able to decrypt this in the future. So you could collect it right now and wait for the time when we have quantum computers. Then out goes the secret. Now, okay. No. Am I going? Okay, plan use for credit cards, same with passports, mobile apps, and VPN. So you could just look at this on your own. But yeah, I've been active in this domain, and yeah, it's heavily it has a heavy usage of ECC and RSA. So once you have a quantum computer, you could definitely be a man in the middle and break the transaction. So your payment, your money will be stolen, your identity will be stolen, things like that. So what are the required qubits? This is from the BSI from Germany. So it's what are the required qubits to actually break an RSA? So more or less, if you have a 1024 bit, more or less roughly twice of that, you could break 1024 RSA bit, and so on and so forth. For ECC, it's roughly 10 times. If you have 160 key RSA ECC key, then 10 times qubits, then you could break ECC. This is logical, not physical. Logical means you assume that the qubit stays as they are, so they're stable. Now, okay, physical qubit is the qubit in reality. So qubit, Bobby's a physicist, so you know that qubit is not so stable. But this is the progress of qubits in the last how many years? 20 years. So what does this curve look like to you? Anyone, could you type in something? Is it linear? How does it look like?
This is exponential.
Yeah, very good. So exponential. So if it's exponential, then we're screwed. So it looks like Moore's law. So you know when it's exponential, so it grows very fast. So well, there's a thing with if you do that particular extrapolation. Now, so what do? We're actually screwed. So shall we panic? So some say that it's 10 to 30 years, but nobody really knows. Okay. The standardization body in NIST, it's funny because I think 10 years ago, or no, 15 years ago, they were saying everyone should actually migrate to ECC. Then after a certain period, they kind of retracted that. They said that, okay, it might not be worth migrating to ECC, but consider quantum resistant algorithms, which they have not yet standardized at that time. So there is a recognition that this is a risk in the future. Okay, now what can we do? We have three options. We do something about it immediately. We ignore it, probably do it later, delay it. Okay, just wait and see, or you do a little bit of something, strengthening the traditional. So what are the three? What do we do out of these three things? So from these options, what shall we do? So it depends. Okay, one of the things I learned from management school, from strategy courses, it's very good to ask the right questions. So we have to ask, okay, what's the nature of our data? So is the data in transit, at rest, public, or private? And these are good characterization. And this is also another characterization from McKinsey Digital. So it's a characterization of the data according to data shelf life, the relevance of the data, okay, and the system life cycle. So for example, I'll be going to the Philippines in August. 20 years from now, that data is not really relevant, right? It's not really relevant. So the shelf life of that is is very fast. Okay. Now, for example, in banking, thing is there are transactions that are relevant, the data that are coterminous with the platform. Like I remember, I don't know if this is true. You could tell me in the Philippines when I was still there. there were banks that were still using mainframes, old mainframes. Is that still the case right now? Or they all migrated to the cloud? Okay, I assume probably it is. And so they are very conservative when it comes to migrating to new platforms. Now if you see this quadrant, this is the very dangerous quadrant, because the data shelf life, the relevance of your data is actually long, and at the same time the platform is still there. So it still will be in use and present in 30 years. So that's a very, very dangerous categorization. So based on this, one should actually formulate the strategy. This is more for decision makers. And okay. Okay. Just another characterization. The number of connected devices or endpoints versus the performance requirement. So this will actually influence the complexity of adoption. One is what type of algorithm you will be using, because will it run in constrained devices, or can it run? Does it require many CPU cycles? So this is very important, and the plus the number of nodes, because you will need to update all those nodes. So it's not sufficient just to update one node. So that adds to the complexity of this. So these are just points for decision makers. Now, but it's important to formulate the strategy to according to those characterization. Okay, now that's the more or less the know why. I hope I was able to convince you why they are important, why this PQC is important. Now I'll tell you the know what. So as Bobby said, there are algorithms that are resistant to quantum computers. Okay, I'll give you four. So the left side, this is the hash base. The first column is hash base. It's based on one-way functions and Merkle trees. Merkle trees are like those that we use in Git. I don't know if you're familiar with Git, and those in IT, of course you should be, because this is source code repo, and this is also used in blockchain. So it's based on the hardness of pre-image resistance problem, so hashes. Now the second one is code base, which is based on algebraic codes. This is something that one borrows from coding theory, and this found its way into cryptography, especially Gopal codes. Multivariate polynomials, which are based on a system of quadratic equations, and this is I listed it here, and it's also one of those algorithms that were submitted to the NIST, and it's based on this MQC problem, which is similar to lattice, but it's quadratic. Now the fourth is the lattice. It's based on a system of linear equation. MQC is based on a system of quadratic equation. Lattice is based on the system linear equation. And it seems easy, right? Linear equation, you could solve it. But let's discuss this later. But from this four, okay, the multivariate polynomial is dropped. It was not considered by NIST due to some certain weaknesses found in its algorithm. It's the general ones. Now the three are actually this this lattice base and hash base are actually now standardized, and this code base is still being considered. So round 4, so it's under consideration. Macalis, it's called. Sphinx is already a standard, and you have these three. Kyber, the dilithium, Falcon is something ongoing, and it's going to be standardized. Okay. Okay, now because 3 out of 4 of this currently standardized, one is ongoing, it is being standardized. So 3 out of 4 is being standardized. They are all lattice, so I'll discuss lattice. It makes sense to spend time more on lattice. So what is a lattice? A lattice is our points in vector space. You could think of them as like in this graph. So you have points. The distances from each other are actually specified by some reference points and the angles between them as well. So these reference points are called basis vectors. This is the mathematical definition. So I leave it up to you to decipher this after this. But that is the qualitative description. So this is you guys, if you already took linear algebra, so this is just the linear algebra form of the lattice. So you have 2 basis vectors, and this slide just says that okay, basis vectors are not unique, so they could actually describe the same lattice. So that's basically it. Now this is a question to you guys, probably as a mental exercise, or if you're going to devise an algorithm. Okay, this is the lattice. Okay, I get a random point in between these lattice points. Find the closest lattice point to that point. How would you actually devise an algorithm? First, when I actually saw this is so easy, right? So I spent my 2 years in physics. This is so easy. I mean, it looks so easy. So the way I will do it is I will actually get the dot product between the basis vectors. So I should have the components, right? So I mean, that's a simple exercise in physics. So this one I will actually have. But actually, if you do the exercise, you cannot simply get a product if it's not an orthogonal basis vector. In linear algebra, a matrix inversion is just the transpose of that orthogonal set of vectors. You cannot just do that. Why? Because given this equation, you have this error term here, most probably this one, and you could see the second term here. If this is not orthogonal, it will be large. So that's why they are called bad basis vectors, but they're good for cryptography. So this is basically the basis of lattice. So basically that's it. I think that sums up basically lattice. And okay, and this one is another variation of the problem, which is the shortest vector problem. Instead of having this point in some random point here, now you have the origin. Get me the shortest vector. It's the same problem formulated in another way. So it's also a computationally hard problem, given a bad basis vector. So okay, now just a segue. When I was actually doing this talk and I was preparing the slides, all of a sudden this researcher came up with a paper which actually rocked the whole crypto world. And it's claiming that it has an algorithm of polynomial time that could break the lattice. So this was actually a surprise to the community. But a good thing in the academic world, if you publish something, it's free for all the smartest people in the world to actually verify it. And surprise, surprise, after 1 week, it's okay, April 10, April 18, boom. He retracted his statement, is saying that okay, I have a bug in my algorithm. I don't know how to fix it. So therefore, yes, hallelujah, lattice is still not broken. So we can still use it. Okay, basically that's it in a nutshell. And the other slides I'm going to present in the symposium, I'll probably just flip it over just to tell you what it is and give you a preview. So in cryptography, we don't use real numbers and integers. We use other number systems. So this is just to tell you that there are number systems like a ring, a field, and a module. Basically tells you that yeah, integers and yeah, there are actually field. But to make the long story short, anything could be a number. A Rubik's cube can be a number, not anything, sorry, but anything that obeys certain rules. Like a Rubik's cube could be a number, and the operation is, for example, this is the rotation of the faces. That could be a number system. Now, in the same way, in cryptography, it makes use of this certain number system so that they obey certain operations. So this is just something that you could look up on your own, and it is very useful when you're actually trying to understand cryptography. This is just my personal cheat sheet, just a review when you actually try to understand more deeper into number theory. So these are some denotations that you will need to have in handy when you're trying to parse papers, unless if you have a very good memory. Anyway, another set of name the picture. Okay, who's this guy? Can anyone tell me who's this guy is? Can you still hear me?
Yes,
Okay.
sir.
Yes, po, sir.
Lord of the
Okay.
Rings.
Yeah. Sir
Okay.
Dylan said Frodo.
Very good. Frodo. This is Frodo. And okay, Opla. Okay, next. What episode is this, and what do you call this episode? You know? No Star Wars geek. Are we too old for Star Wars? Okay, Star Wars. This is episode 4. This is New Hope. And okay, who's a Trekkie here? Star Trek. So this is Spock. This is what's this other Scotty? So they're doing something. They're installing a crystal. Do you know what this crystal is? Okay, it's the crystal. It's called dilithium. Okay, I just flashed these pictures just to probably show you that the cryptographers they do have sense of humor. I'll just go forward, skip the slides. So LW is just another name for lattice. So the cryptographers do have a sense of humor, and they actually name their algorithms according to these pictures. And it's either they have a sense of humor and they maintain this geeky footprint. So Frodo is named for a plain ring. So Lord of the Rings, go figure, right? So when it's used, the ring as a basic number system. And the New Hope is an evolution of that. Instead of plain rings, it uses polynomials. And this was done by a very prominent cryptographer in the company I work in. So it was actually adopted by Google. In the browsers, it was experimented for a time, then it was pulled out. And the other one is from the very famous Regev, the guy who actually proposed lattice as a crypto system. So this is dilithium. These are the lithium crystals. So we know that he's a Star Trek fan, and we know that this guy from my company is a Star Wars fan. Anyway, that's it. And what are the others? I think this is not relevant for the group for now. Kyber is the key encapsulation mechanism, which is an alternative to what Bobby actually proposed. And discussed. It's a key. He did a quantum key distribution. Kyber is a post-quantum way of encapsulating the secret via lattice problem. So Kyber is standardized. Dilithium is standardized. So these are the keys. And okay, that's basically it. This is something close to my heart, but I will not discuss it here. Okay, so NIST, okay. NIST is a organization. It's a standardization organization in the US. Basically, it's very influential. When they say something, especially in cryptography, other standardization bodies they follow, or they more or less try to follow the lead. I have first-hand experience in this when I was in France, and they have their own ISO, and also in Germany they follow this very much. So if they standardize certain algorithms, they will more or less follow the lead of this, although it's just for the US. Now this is just the timeline of that, this PQC standardization. To make the long story short, these are the standards right now. So we have the tree, the lithium, and you have this hash base. I forgot what was the name of this. I forgot, but this I mentioned this the slide. So this is the hash rate, and there's another one upcoming which is based on also lattice based, which is Falcon. It's another lattice based crypto system based on N-True. Okay, now I hope I didn't confuse you by just flashing you this equation. I didn't want to go deeper there. I just wanted to give you some mental anchors just in case you were going to into this field. I hope I was able to convince you why PQC is important. That's the first point. Second is PQC is accessible. So Bobby's math is a lot more complex than the math that I showed. Okay, this requires just basic number theory, abstract algebra. So it's very conceptual. You could actually understand it. It's just you need patience to go through this to this notation, but underneath is actually a very simple concept. And of course, I'm downplaying all the complexity, but the entry level interesting concepts is not is very accessible to anyone who's very interested. And you don't need a quantum computer to do this. You could basically implement PQC cryptography in a constrained device. Okay, then the last point is probably for saying that why this is cool. 1.5 years I went to Paris because I visited this French startup which was doing some very interesting work on lattice-based homomorphic crypto system. So they organized this barbecue thing. It's a small startup. So I was there, and the thing is, it was just in a small office, like a coffee shop. It's a bunch of PhD rock stars sharing work over barbecue. Very cool guys. Fast forward to this year, I think last month or 2 months ago, press came out. They received 70 million euros of funding in one round. So that's big. So that's the biggest funding of a French startup in one series round in French startup history. So to close my talk, this is why I think lattice or cryptography right now along this direction, and not just lattice, post-quantum cryptography is very cool. And if you actually find it interesting, I think you could change the world and be the next guys like those guys in this French startup. Okay, thank you. And I'll end my talk now. Thanks for listening.
Thank you po, Sir Earl. So, let me share screen. I'll just
How
share
do
my
I
screen.
remove the... I got missed. Okay, good. Sorry,
Okay.
it took some time, right? How 45 minutes, that's too long. Okay.
So now we'll be having a Q&A portion. So you can send your questions using the Slido link. So kindly go to the meeting chat. Okay, so to access the Slido link, so you can send in your questions. So for question,
Yeah, it's Sphinx. I thank you, Dylan. I missed that Sphinx. Yeah.
okay, so yeah, we have our first question po, Sir Bobby and Sir Earl. So how can we use PQC for high dimensional real-time streaming data streaming data like videos, audio, or satellite imagery data in transit?
Well, PQC is just an upgrade of the algorithms, meaning whatever you have right now, it's just in principle they are substitutable. It's just that they are actually they have more space and they have more bigger key sizes. Is the same. I mean, when you say how, there are different ways of answering these questions. How specifically, I would you would need to go through all those algorithms, and I would probably refer you to website of Microsoft. Microsoft has a good library, and who else? Cloudflare has a good set of libraries, and these are open source, and you could use them. And there are plenty of libraries that are open source for different platforms. So I cannot actually answer this question in detail without knowing the specific application space. But that's where engineering comes in. Actually, an engineer tries to fit the use case with the technology, right? So it's not a question that you could just say one blanket reply. Yeah.
Okay, thank you po, Sir Earl. Okay, so now let's move to another question. So sa agreement, is that through quantum din? Yeah, yeah. Or yeah, if ever,
What question are you? This versions of classic computers, like computation, or is it
yeah,
what is
yeah,
the most suitable quantum cryptography solution for securing IoT? I think it's okay. Sorry, what are they called?
yeah. I think for this one, it's if whoever sent this question po, can you
It's for Bobby.
Sorry. I was actually trying to understand it, question as well. Sa agreement, is that through what's
Probably key agreement.
yeah,
oh, okay. Key agreement. Okay, so in the protocol, it's the agreement is via the is tama no? This one is QKD. So let us say assuming that this is the QKD question, they agree kasi when the when the photon is is sent in a particular orientation, no? So dalawa lang naman yun eh. It's either rectilinear or diagonal. And then Bob um, was lucky enough to pick the right ano um, the correct basis to measure, then nag-agree na yung ano doon, yung ibig sabihin what Alice sent was really the qubit value, whether 0 or 1, is what Bob will ano Bob will get, no, theoretically. Pero they still have to determine if tama nga ba talaga, no? So that's why they will have to get a subset of their qubit photons, no? And then Alice will say this photon number 1 is actually a 0, and then Bob will determine if he got a 0 or not, no? So kapag Bob got a different, kasi ideally that 0 din nakuha ni Bob, no? Pero if it turns out to be different, then it means that someone tampered with with the communication. So quantum siya. Quantum plus human. Kasi they have to announce through the public, no? In whatever way, no? Through the telephone, through chat, no? Public, there's nothing encrypted there, because that's the way they will seek agreement.
Bobby, probably I'll add, if, for example, this refers to post-quantum cryptography, yes, there are post-quantum cryptography algorithms that could be based on those that I mentioned that tries upon the key encapsulation mechanism. So this could be also non-quantum. Basically, what is key agreement? Both sides, Alice, Bob, they find a way to actually agree upon a shared secret without someone in the middle being able to derive what that key shared secret is. So that's in a nutshell. That's what it is. So you could do it the QKD way, and you could do it through non-quantum means.
Yeah, thank you po, Sir Bob and Sir Earl. So, yeah, I think for the next question,
This one, this IoT solution. I think, how do we go from this? Up or down? How do you,
I think
okay.
we have to go muna siguro from bottom up.
Bottom.
Kasi yung
Ganun pala.
bottom is
Okay.
yung pinaka
It's not a stack. Okay, FIFO.
it's
Okay.
a stack. Okay, that one. Hello, I would like to clarify the L. Okay, so the one that I showed earlier, which is a practical example of one-time pad, no? So yung alphabet mo doon, those are yung mga letters, numbers, and punctuations, no? And suppose you put them in an array, then the size of your array is corresponds to L. Yeah, so the size of your array corresponds to L, or the number of characters. Okay, you're welcome, Ethel.
okay, thank you po,
Okay.
Sir Bobby.
Dyan naman, how can Alice and Bob use cryptography in dealing with Eve? Okay, so actually may dalawang may dalawang two ways you can do this, no? One is what is known as the public key public key
PKI.
infrastructure, no? O PKI, or yung tapos yung isa naman yung kanina, which is using the quantum key distribution. We use the properties of quantum collapse of wave function and no cloning theorem in order to determine na if there's a eavesdropper. Kasi normally we don't, for example, we are in the classical world right now, diba? Classical computing. When I send a message to someone, no, I will never know if merong eavesdropper. You know why? Because anyone can just clone my data. Anyone can just copy. No, for example, we copy DVDs, we copy videos, no, all the time, no, copy files, no, and no one knows that we're copying. Pero in the quantum, in the QKD, once you copy, you destroy the state, no, it becomes different state. So, yun, that will, yun yung magagamit mo sa, ano ba yung inano ko dito? Doon sa, one way to keep your message secure, no? When a eavesdropper is there.
Thank you po, Sir Bobby. So I think this one will be our last question po muna. For other questions na hindi po ma-entertain tonight, we will be sending the answers together with the notes and the certificates na lang po. Okay, so for the last question, um, is there a possibility to use or run the short algorithm on classical computers?
No.
Actually, depende, no? If you have 15 cube, if you have if your number is small, yes. For example, you can run
Yeah,
it
pero hindi sila parallel, di ba? They're not. It's just a simulation of the
simulation
QFT.
lang. Oh, simulation.
Simulation. It's not the real. It's not the
Oo.
real Shor algorithm.
Oo.
But yeah,
So,
you could simulate it.
oo. So ibig
But
sabihin, if you run it on a classical computer, for a 2048 bit encryption, it will take you the time of the universe, no? For imagine lang, no? 50 qubits. 50 qubits, uh 50 qubits will take you 2 to the 50, will need 2 to the 50 memory space, no? But 2 to the 50 is about 1 petabyte of memory, no? Eh, memory lang ng laptop ko is 32 gig, no? But 1 petabyte is very big, no? So, even a 50 qubit number, you cannot run Shor's algorithm na efficiently, no? You need to have very big resources on a classical computer.
Okay, thank you po, Sir Bobby. So, yeah, I think that's all for our Q&A po muna. And for other questions, keep the questions coming. We will be answering the questions and we will be sending the answers to your questions together with the certificates and the notes. Okay po. Okay, so now after the Q&A, first let's have award the certificate of recognition. Okay, so One Quantum Philippines awards the certificate of recognition to Bobby Corpus for sharing his valuable insights on the quantum key distribution and post-quantum cryptography lecture event organized by One Quantum Philippines, a virtual discussion initiative on May 4, 2024. Signed by Menchi Bellarmino, Associate Program Manager, and 𝒂𝒏𝒕𝒖𝒎, Director of Operations. Okay. And another one.
Maraming
So,
salamat.
yes. Okay po. So, One Quantum Philippines awards the certificate of recognition to Earl Robles for sharing his valuable insights on the quantum key distribution and post-quantum cryptography lecture event organized by One Quantum Philippines, a virtual discussion initiative on May 4, 2024, signed by Menchi Bellarmino, Associate Program Manager, and 𝒂𝒏𝒕𝒖𝒎, Director of Operations. Okay, so
thank you very
now,
much.
yes. Okay, so now, before we officially end, we will be having some announcement lang po to everyone. So, One Quantum Philippines will be opening the Quantum Education Fellowship Cohort 2. This is a volunteering experience to help us expand our impact in empowering Filipino talents in quantum science and technologies. Applications will open on May 12 to 18. So for to be more updated to these to this event and also our future events, please follow us in our social media platforms. So for Facebook, we are onequantum.ph, and in LinkedIn, onequantum.ph. Okay. Okay, so now, may I ask everyone to please open your camera for a photo opportunity. So, yeah. requesting everyone to please open your camera po for a photo op. Okay, so yeah, Menchi, can you take a screenshot for our photo op?
Let's remove the screen share for a bit. Okay, so I will be taking screenshot for 2 pages. First page, and 1, 2, 3. Okay, and then another screenshot for the second page. 1, 2, 3. Okay, thank you so much.
Salamat.
Okay,
Okay, thank you.
so yeah, before we end, so okay, wag po muna tayong umalis. Ayan. So to claim your e-certificates, we are requesting everyone to please answer the feedback form. So you can scan the QR code or go to the link to this link to access our QR code. So the feedback is one of the requirements for the e-certificates. So yeah, we are highly encouraging everyone to answer this feedback form, and as well and also it will help us to um improve to help us know what are the things to improve in our future webinars and events. Okay, so the link for the feedback form is in the chat box as well. So yeah, you can use that aside from the QR code on the screen. Okay, so yeah, so again, thank you everyone for attending the quantum key distribution and post quantum cryptography lecture today. And yeah, we highly appreciate your flexibility and for joining us kahit na nag-extend tayo ng 1 hour. So yeah, thank you everyone, and please don't forget to don't forget to answer the feedback form.
Thank you.
Yeah,
Thank
thank you.
you. Good evening.
Good
Thank you
Bye.
very much.
Thank you.
Bye.
Yeah, Menchi, I just have one clarification. We'll be sending recordings to our participants.
Oh yeah, about the recordings, we may have to delay the recording until a month after. So if you're patient to wait for a month, then you will be receiving the recording for the full lecture, including the notes and all other resources used in the lecture.
Yeah. Thank you, Menchi.